Okay, you should be at standard S1, and I've written some stuff, so you'll probably need to pause every once in a while in order to make sure that you're getting all of your information. So we've been working in the last couple days on introducing different patterns and how to logically go about finding a rule for that pattern so that you don't have to figure it out the long way every single time. We've worked with sequences and series, but have not yet defined them, so that's where we're going to start. There are two kinds of sequences, arithmetic and geometric, but we're only going to focus on the geometric for this standard. Okay, so a geometric sequence is a function which gives a list of numbers based on position whose ratio of any term to the previous term is constant. A couple of things, when that word ratio comes up, that means fraction. This is like when you were finding the rebound ratio, and you had to take the rebound height and divide it by the previous height. This is what you were finding. You were finding a list of numbers where that ratio is pretty much constant from one rebound to the next. I'll give you a minute to write that down. One thing I did add in here is that the common ratio is usually written as an R. So in these problems, R doesn't mean radius of a circle because we're not really working with shapes. R would mean the ratio. And then for series, a geometric series is when you add up all the values in a geometric sequence. So it's basically taking all your numbers that would be listed out that have that common ratio and adding them all up. As you've seen from our practice work, if there's a pattern, you can write a rule for it. These rules are helpful on multiple levels, but mostly because you can cut down on the amount of work needed to solve a problem when you form a rule for the existent pattern. When the pattern follows the geometric pattern, which is this ratio, this constant ratio that happens when you divide a number by the previous number, the following rules for sequence and series is the following. So for a geometric sequence, the nth term, which means like, I don't know, the 10th term or the 12th term or the 4th term, whatever term in a geometric sequence, when the first term is given by a sub 1, and you know the common ratio, this rule would be how you would set up the rule for that geometric sequence. So if you have a common ratio and you know the first term, you can set up the rules to find any term in that sequence, no matter the position. So for an example, the nth term of a geometric sequence with a first term of 3 and a common ratio of 2 is given by this expression. So if you know the common ratio is 2, you plug that in for R, and if you know the first term is 3, you plug that in for a sub 1. And then this rule would give you the value, is like if I wanted to know the 10th position number, I'd plug in 10, and then punch it out to get the value at that position. When you're writing, you might need to pause it, but when you're ready, go ahead and flip. Okay. So for example 1, we're going to first work with each A, B, and C and determine, first of all, if it is a geometric sequence, and if it is, we're going to write a rule. If it's not, we're just going to stop. So to see if it's geometric, we start dividing each number by the previous term to see if we get a common ratio. Okay, so let's start by 10 divided by 4. 10 divided by 4 would reduce to 5 halves. Then you do 18 divided by 10. So 10 divided by 4, 18 divided by 10. 18 divided by 10 does not reduce down to 5 halves, but it does reduce down to 9 fifths. 28 divided by 18, that also reduces down to 14 over 9. And I'm going to stop there, because since these values are not the same, this is not a geometric sequence. There's probably a rule that you can find that would give you those values at every position, but it's not going to be a geometric type of sequence. So your common ratios don't match. So this is not a geometric sequence. Okay, so you do something very similar for the next problem. I usually start with the first and second term, and I'm going to take 125 and divide it. Sorry, I lost my page here. Let's get my next problem. You're going to take 125 and divide it by 625. If it can reduce, do it. This one reduces to 1/5. Then you take 25 divided by 125. That also reduces down to 1/5. And then just for good measure, let's check the next one. 5 divided by 25 gets me 1/5. Okay, that's enough to check. I have a common ratio. They do match. So this is a geometric sequence. So to write the rule, if you look previous page here, my rule is going to be the first term in my sequence times the common ratio raised to the power of n minus 1. This is exactly what we're going to write here. What did I write it as? A sub n. A sub n, which that just represents this is going to be a sequence rule or sequence equation. First term is 625 times the common ratio, which is 1/5, to the n minus 1. Okay, so you first have to check to see if it's geometric by finding the ratios. If they match, then you can write the rule. If they don't match, then you just tell me they don't match, and you have to show some work to show that they don't match. Okay, let's go ahead and do the other one. So 81 divided by 27. That reduces down to 9. Actually reduces down to 3. 27. Oh, sorry, I did that wrong. 27 divided by 81. There you go. That reduces down to 1/3. 9 divided by 27. That reduces down to 1/3. 3 divided by 9. That reduces down to 1/3. Okay, that's enough to check. My common ratios match. So I'm going to write my rule. A sub n. First term is 81. Common ratio is 1/3 to the n minus 1. There's my rule. So again, if I wanted to find the 10th number in this sequence, instead of figuring out every single one, I can use this rule, plug in 10, and find the 10th number without figuring out 10 numbers in a row. I just want to jump to the one that I want. Okay, so this is part of the standard, is being able to identify if it's geometric or not, and then write the rule if it is. And then the other part is working with the geometric series. Remember, series is working with a geometric sequence, so something that looks like this, right here. And then the series is adding them all up. So the sum of the first n terms, so I would ask you to add up maybe the sum of the first 20 terms of a geometric series with a common ratio. You can't have a common ratio of 1, so I just have to throw that in there. But the sum formula for a geometric series is a sub 1. Remember, that represents my first term. So maybe you want to write that. First term. The r is my common ratio. And the n is the number of terms you're adding up. Now again, we could figure this out by hand by, if I wanted the first 20 terms, if you list out all 20 terms, and then I add them all up. But if I have a rule that does it for me, this cuts down on the work tremendously. The other part of it is this sigma notation. This is how they kind of set up the problem for you. The LL represents your lower limit. This is your a sub 1. The upper limit is your n, or how many terms you're trying to add up. And then your rule that you're going to use is right here. So an example would be, I want to add up all the terms from, I should not have that as term 1. This is the first position you're adding up. Okay, so So first position you're adding up all the way to 16. So I'm trying to add up all the numbers in positions 1 to 16 that are given to me by this rule. Okay, and we're going to do two examples like that. So here's example 1. We're going to find the sum. This is one that I just wrote down. Of the first 16 terms. Since I want to find the sum, I'm going to write the rule for the sum of a geometric. I know this is a geometric because it's set up as a geometric where you have a sub 1 times r to the I minus 1. So a sub 1 minus r to the n, or 1 minus r. Checking. Yeah. Okay. I want to add up the first 16 terms. So actually, let's do s sub 16. My a sub 1 term is that first term in my rule. So my a sub 1 term is 4. My common ratio is the number in parentheses there, so it's going to be 3. Then I want to add up to 16 terms. So you should have 1 minus 3 to the 16th as your first statement on the top, and then on the bottom you'd have 1 minus 3. And then at this point it's just punching it out on a calculator. So, I don't know where my calculator went. There it is. So 4 times 1 minus 3 to the 16th divided by 1 minus 3. Notice I put the top in parentheses and the bottom in parentheses. Punching it out gets me that value. So 86,093,440. So 86,093,440. That's going to be pretty common that the sum of your series, especially when you get up into double-digit terms, is going to be quite large. Okay, so let's go ahead and do example 3. Find the sum. Here's my rule, my geometric rule. This is my n, or my number of terms that I'm adding up to. Here's my a sub 1, first term of my series. Excuse me, and here's my common ratio. So we have s sub 8. I'm going to use the same rule as I did up here. So a sub 1, first term in my series is 6. We have 1 minus negative 2 to the 8th over 1 minus the negative 2. And then punching it out. Make sure you put the negative 2 in parentheses. Gets you negative 510. And that's where we'll leave off. So this is Crisscross signing off.